Hello, I am coming to you to present our energy practice problems, working it out for you on YouTube. I've got three equations here that we're going to use today. I've got work equals force times distance, potential energy equals mass times gravity times height, and kinetic energy is equal to 1/2 mv squared. As we've discussed in class, we'll be able to set all these equal to each other for different types of problems. The work done to lift something up to a certain height is the same as the potential energy it gains. The work done to increase the velocity of something in a horizontal direction is equal to its kinetic energy. And finally, we can convert potential energy into kinetic energy as something is falling, or kinetic into potential as something is moving upward and losing velocity as it gains height. So let's get started. A monkey hanging out in a tree 6.4 meters above the ground drops a 0.25 kilogram coconut. What will the speed of the coconut be just before it hits the ground? We have a height of 6.4 meters. We have a mass for the coconut of 0.25 kilograms, and the question is, what will the speed of the coconut be, which of course by now we're used to calling velocity. So we have enough things here to not find the velocity directly, but to find something with our energy equations. We have mass and height, and from that we'll be able to find potential energy. So let's think about what's going on as the coconut is falling down to the ground. When it's up at its height of 6.4 meters, it has all potential energy, and when it's right down at the bottom, just before striking the ground, it's got all kinetic energy. So that means our PE is going to be equal to our KE, or potential energy equals kinetic energy. Let's find our potential energy first. Mass times gravity times height. So that's going to equal 0.25 times 9.8 times 6.4. And of course, you can use 10 if you'd like to. I'm calculating on the fly. Hold on. All right, I got about 16 joules, 15.68, and you can leave that unrounded if you want to. So that is also equal to our kinetic energy. Oh, I'm sorry, I'm writing out of frame. So if our kinetic energy is equal to 1/2 mv squared, then we can say 16 equals 1/2 0.25 v squared. To solve this problem, we have to do some stepwise algebra. Most people like to multiply the 1/2 times 0.25 first, which would give you 16 equals 0.125 v squared, and then we can divide both sides by 0.125, and we'll get about 125 equal to v squared. So then hit the square root key on your calculator, and you'll get about 11 meters per second is equal to our velocity. A dog does 8.3 joules of work lifting a 6.8 Newton bone up onto his bed. How high is the bed? So this problem only gives us a couple numbers, but let's label. We've got the work, and then we have this 6.8 newtons, which is a little odd, but that is the weight of the bone. So they've given us the weight of the bone, and it's in newtons. So if you recognize that it's in newtons, even if you're not quite sure what to do with it, go ahead and write that down as a force. And we're looking for how high the bed is. So if you can see that as a force, even if you're not quite understanding how it's related to this equation, you will see that we have work, force, and we're looking for distance, and that appears to be our work equation. Work equals force times distance. The reason that this bone weight is the force is because the dog is lifting that bone up onto the bed. There's my bone. And the force that they're going to use to lift that bone up onto the bed is the 6.8 newtons. So if the bed is this high and he lifts it all the way up over here, he's got to use that force the entire distance. So that's why we can use that for work. Our equation, work equals force times distance, and we have 8.3 equal to 6.8 D. All we have to do to find the distance is divide both sides by 6.8, and we will get 1.22 meters. The second question for number 2 is, if the bone falls off the bed, how much kinetic energy will the bone have just before striking the ground? When the dog lifts the bone up onto the bed and does 8.3 joules of work, he gives that bone 8.3 joules of kinetic energy. So if the work equals 8.3 joules, then so does the potential energy. If the bone has 8.3 joules of potential energy at the top of its bed and it falls, it's going to turn that potential energy into kinetic energy. So that is also equal to the kinetic energy at the bottom. And I'll just put here that that's the potential energy at the top. So the answer is 8.3 joules. Number 3, we have a skier who slides down a frictionless ramp from the ski lift and has a velocity of 3.3 meters per second at the bottom of the ramp. What is the vertical height of the ramp? This question seems a little bizarre because they give us one number and they want to know a height. When it comes to energy, you just have to remember, when in doubt, you need to remember to set one energy equal to the other. I'm going to draw a picture over here of my skier who's going down the hill on her skis. At the top of the ramp, there's the height of my ramp. At the top, she's got only potential energy. And at the bottom of the ramp, she has converted all that potential energy into kinetic energy. So just like we saw in number 1 up here, we're going to set potential energy equal to kinetic energy, because all her PE will turn into KE. Since we have so little to work with, we only have a velocity. If we look at our equations here, that's in the kinetic energy equation, but we don't have any of these other numbers and we're looking for height. So when this happens, I want you to trust the math, and I want you to go ahead and write these out in their variable form. If mgh is equal to 1/2 mv squared, that's the equation for potential energy. This is the equation for kinetic energy. Then we can cancel out the m's. When we do that, we end up with GH equals 1/2 V squared. And we know gravity and we know V, and we can find our height. So it's kind of a weird looking equation, but we can figure this out. We're going to plug in and we're going to solve. So 9.8 times H, which is our unknown, is equal to 1/2 V squared. When we solve this, I want to remind you, take the 3.3 squared, do that first, then divide by 2. If you take half of 3.3 and then square it, you're not going to get the right answer. The order of operations is that 3.3 has to be squared first. So that's my next step. And now that we've got 9.h equals 5.445, we can divide both sides by 9.8. The height of our ramp is 0.56 meters. Number 7, a 7.5 kilogram watermelon is dropped from the roof of a 14-meter building. So we have a mass of 7.5 kilograms, and we have 14 meters would be our height. And the question's asking for potential energy. Well, this seems pretty straightforward. We know the potential energy is equal to mass times gravity times height. So we plug our numbers in, and we get, oh, I did not get a right number, hold on. That's better. 1,029 joules. In B, it asks what, oh, sorry, I scooted my camera. In B, it asks what is the potential energy at the halfway point of its fall. So in class, we talked about this. We dropped some things off roofs. I think maybe a person, I don't know. And we discussed, oh, that building's kind of curvy. Let me try that again. So if the entire height of the building is 14 meters, and we know that the potential energy up at the top is 1,029, this is a watermelon. It looks like a UFO. Then at the bottom, we know the kinetic energy is going to equal 1,029 joules because potential energy will be converted into kinetic. At the halfway point, we're going to have half potential energy and half kinetic energy. Because when we add those two together, we want to get that same total value, 1,029. So all we need to do to find this out is take our 1,029 and divide it by 2. We will get 514.5 joules. In part C, they want to know the velocity of the watermelon at the halfway point. So not at the bottom, but right here at halfway. We have the potential energy is 514.5 joules. And we said that it's going to be half potential. That's going to what we found here. And the other half is going to be kinetic. That's what we're going to use here. So this potential energy is the same as the kinetic. And then we can use our kinetic energy equation, 1/2 mv squared, and we can find out what the velocity is. And I'm going to plug in my watermelon mass. That's a really big watermelon. I'm going to take half of 7.5, and that's going to be 3.75 v squared. So now we can divide both sides by 3.75. Almost there. I know these have a lot of steps algebraically. but keep practicing and you'll do them much faster eventually. And then we take the square root. And we get the velocity of our watermelon to be about 11.7 meters per second. In number 5, we have a drag racing funny car. It sits at the starting line. When the light turns green, it achieves a velocity of 32 meters per second along the 200-meter track. So we have a few numbers to work with. We know the mass is 150 kilograms. We know that the velocity is 32 meters per second. And we know there's a distance of the track, 200 meters. The question is how much work was done on the car to get it to this high velocity. Let's look at our equations. We have work that's equal to force times distance. But if we compare that to what we have to work with, we'll see that we don't have force. We only have this distance of 200 meters. Some people get confused and they feel like that they should take the weight of that drag racing car, multiply 150 times 9.8 to get a force. But that's not going to work here because the car's traveling on a horizontal surface. We're not lifting the car up. So we can't use that as a value, as a force in our work equation. But there's another way that we can find work. In this problem, the work is going to equal the change in kinetic energy that our car experiences. So if you recall at the beginning, I said sometimes we could set work equal to kinetic energy when the work was being done to increase the speed of a car. So what we can find using our mass and velocity is the kinetic energy. Our change in kinetic energy is really the final minus the initial kinetic energy, but the car starts from rest, so it doesn't have any initial kinetic energy. That's just 0. So we're going to take 1/2 mv squared, and we are going to find the kinetic energy. That is a big number, 76,800 joules. And then that is also equal to the work that was done on the car to get it up to that speed. The last problem on this side of the page is for number 5 also. What was the force exerted on the car during this race? So it's a force question, and the only equation we have that has force in it is the work equation. We just found the work in part A. So now we can set work equal to force times distance, and we're going to use our distance actually down here in B. So the work done was 76,800. That's times force times distance. So we'll divide both sides by 200 to find our force. 384 newtons. Our last page, let me make sure I can get it in the frame, is number 6. We've got Tarzan. Tarzan runs through the jungle with a velocity of 12 meters per second. He grabs a hanging vine to swing up into the trees. What height does Tarzan reach? So V is 12, and we want to know the height. It's another question where you aren't given many things and they still want you to find something. I want to remind you that we had the same problem in number 3. We were given the velocity and we were asked to find the height of the ramp, and we are in the same boat. So what do you think? You think we'll do the same thing? Let's think about Tarzan running and swinging on a vine. If he is running as fast as he can and grabs onto that vine and then ends up hanging onto the vine up here in the air, That means at the bottom, he's like a pendulum. At the bottom, he has all kinetic energy. And at the top, where he comes to rest, he's going to have all potential energy. And then the height that he reaches is going to be part of that potential energy equation. So we're going to convert KE into PE. And since we don't have many things to work with, we're going to make these as detailed as we can. We're going to write all the variables in, and we're going to say hooray when our mass cancels out and we have a simplified equation. So we have the V and we know G, so we can easily find H. So this will end up being 1/2 times 144. So square the 12 first and then divide by 2. And we'll get 72 equals 9.8H. And then we'll divide both sides by 9.8. My son is watching a very loud movie, and if it is disturbing this calm physics video, I apologize. So the height that he achieves in his vine swing is 7.35 meters. In question 7, a snowboarder in a half pipe drops in at a height of 22 meters. If he only gets up to a height of 20 meters on the other side of the pipe, how much energy was lost to friction? So we have two heights. We have a height, and you can call it an initial height of 22 meters, and then we have a final height of 20 meters. And we're asking about the energy lost. Now this is a new question. We haven't done one like this. I'm going to draw over here in case some of you don't know what a half pipe is. It's shaped like half of a pipe, and there's a snowboarder, and he drops into the half pipe, and he's going down like this. So he's at an initial height of 22 meters, but on this side he only makes it up to 20 meters. And that means if energy was conserved perfectly, he would go all the way up to 22, but he didn't quite go to 22, he only made it to 20. When you're doing energy loss, one easy way to do it that won't get you confused is just to find his initial potential energy using MGH, and then you can find his final potential energy using, I'll put initial, using MGHF, and then we'll subtract the two. That's the fastest way to do it. Oh, hold on a second. I think I forgot to give you a number in this problem. My video cut out on me. Luckily I caught it before I got too much further. But I did end up finishing this problem without you before I realized the video wasn't on. I think I was realizing that I did not give you the mass for this question number 7. And so I've added a mass in. 70 kilograms. Let's make it 70. And that allows you to find his potential energy. So I plugged in his mass and gravity and height for both situations, his initial and his final where he ends up. And I found two potential energies, 15,092, a little higher, and then the 13,720, he's a little lower, so that makes sense. We subtract those two, and you end up with 1,372 joules, which is the difference in his two potential energies. That is the energy lost to friction and whatever else was going on as he went through the half pipe. The alternative way to work this out would be to subtract the two heights and get a height difference of 2 meters And then you could plug that into one equation, mass times gravity times height. You would come up with the same answer if you plugged in 2, did 70 times 9.8 times 2. This would be the answer. So you can work that either way. It's correct both ways. The final question is a UPS sorting facility question. We have a box that's released at the top of a 4-meter height curved ramp. When it reaches point B at the bottom of the ramp, it encounters concrete and comes to a stop over a distance of 10 meters. So there's a lot going on in this question. The first question is, what is the potential energy of the box at the top of the slide? We know that potential energy is equal to mass times gravity times height. So let's see if I gave you the mass of the box on this problem, because I seem to have forgotten some things on this worksheet. Let me see if I can figure this out. Look, it appears that I did not give you the mass. So I'm going to make up the mass of the box and say that this box is 2 kilograms. So I will write that in and email you all and let you know. Okay, mass is 2 kilograms, gravity 9.8, and the height of the box is 4 meters. So we can find potential energy. It is mgh. So 2 times 9.8. And again, I'm using 9.8. I don't know. I get on a kick. I don't know why I'm using that tonight instead of 10, but feel free to use 10 if you would like. I'm going to count them both correct. That would be 78.4 joules of potential energy at the top of the slide. What is the kinetic energy of the box at the bottom of the slide? Sorry, I'm looking at a camera. I was looking at a camera function to see what was going on with my camera. So we have at the top all potential energy and at the bottom all kinetic energy. So that means that whatever our potential energy was initially, it is equal to our final kinetic energy. So the answer is 78.4 joules. Easy peasy. On question C, they want to know how much work was done on the box to bring it to a stop. So in this section right here, we have a change in kinetic energy. The kinetic energy at position C is equal to 0. So our change in kinetic energy, or KEF minus KEI, this is a little strange because here I put that the final kinetic energy was 78.4, but that was for the sliding part. So now this is going to be our initial and that's going to be our final. So we have 0 kinetic energy at the final position minus 78.4 joules initially, and that gives us an overall change of kinetic energy equal to negative 78.4 joules. Now the negative is somewhat important because it means the box is going to come to a stop, but if you don't put the negative in there, that's not a huge deal to me on the test. So that is, oh look, I just drew a box around it, but I didn't actually tell you. I was looking for work, but just like we saw earlier in the worksheet, the work is equal to the change in kinetic energy. So this is also, equal to work. And our last question. What was the force acting on the box to bring it to a stop? Well, we have the work. We just found that in part C. Negative 78.4 joules. We have in the picture and in the problem, they gave us the distance that's going, which is 10 meters. And we're looking for the force. So that's our original equation, work equals force times distance.